Today we're going to focus on section 3.2. We are moving to a bigger group of functions, polynomial functions and their graphs. Now, just to give you a heads up, messing with the adjustment, there we go. Our quadratic function is an example of a polynomial function. So things that are true for our quadratic functions in general are going to be true for all polynomial functions. For example, we only have a polynomial function if the domain includes all real numbers. Notice I didn't say anything about the range, just the domain. If the domain includes all real numbers, we could have a polynomial function. Now, if there are limits on your domain, it's not polynomial. If there are limits in the range, doesn't matter. But we're focusing on domain is all real numbers. The shape of your graph. The shape of the graph is going to be all smooth and continuous curves. No gaps, no holes, no sharp corners, no breaks. Because of this, for example, our absolute value function, it has a domain of all real numbers, but because of that sharp corner, it is not polynomial. Sharp corner, so not a polynomial function. Not a polynomial function, not a smooth continuous curve, okay? All right, third characteristic. All terms in our polynomial function are going to have positive integer exponents. So the exponents on the terms are going to be whole numbers that are not negative. So it's all going to be 2, 4, 5, 6, 7, 8, 9, 10, 11, 12. You're not going to have any exponents that are negative, and you're not going to have any exponents that are fractions. Always positive integer exponents. Okay, so remember that anytime I see f of x, that's a function value, a y value. So these represent two different y values, the value of the function at a and the value of function at b. If they have opposite signs, so one is positive, one is negative, if you have two function values that have opposite signs, one is plus, one is minus, then I know that there is a zero or root, also called an x-intercept, between them. Which makes sense, right? If I plug in some number and I get out a positive value, and I plug in another number and I get out a negative value, I had to have crossed the x-axis, which means that there is an intercept, a root, a zero, between those two x values. And then the last of our 5 characteristics that we're going to list, the greatest possible number of turning points is no more than or up to 1 less than the degree. Now, what's a degree? Well, our quadratic function is second degree because the biggest exponent is a 2. Our cubic function is third degree because our biggest exponent is a 3. So the degree is the exponent, the largest exponent on a term. The degree is the largest exponent on a term. Okay. Now we're going to have a bunch of theorems in this unit. I think we have 2 or 3 today. The first one is the intermediate value theorem. Now this is something that you kind of have always used and just known intuitively, but we're going to get used to some mathematical language this semester, and this is the start of that. Our intermediate value theorem, IVT, says, suppose that f is a polynomial function, and you have an interval on the x-axis. So I have some x value a, move over to some x value b. It is an interval for which the function values, the y values that you get, are not the same. So if I plug in a, I get one answer, and if I plug in b, I get a different answer. if I have a number between these two function values, and we're going to call it L. Let's say L is some number between this y value and that y value. Then that means that there is a number, let's call it C, inside that interval, so that if I plug it into my function, I get out L. Basically, what this means for us is that we can connect the dots. We don't have to find a million points to make our graph. We can find some points, know the general shape, and then we can connect the dots. You ought to know the graph of this cubic function. It's one of our parent functions that we've focused on. We know the general shape of that cubic function. I know that my cubic function goes through the origin. I know that if I plug in a 1 and I cube it, it's 1. If I plug in a 2 and I cube that, I get 8. So 1 cubed is 1, 2 cubed is 1, 2, 3, 4, 5, 6, 7, 8, way up here. Now I just found 3 points on my graph. 0 cubed is 0, 1 cubed is 1, 2 cubed is 8. My intermediate value theorem tells me that if I know I was able to plug in 1 and get 1, and then I was able to plug in 2 and get 8, there is a number that I can plug in between 1 and 2 that's going to give me each of the values in between on the y-axis, 1 and 8. So that what I can do is I can connect the dots and fill in my graph. Let's see, -2 would be -8, 1, 2, 3, 4, 5, 6, 7, 8. So the intermediate value theorem lets me take this point and plug in, without plugging in, excuse me, connect those dots without having to find an infinite number of points in between. Okay? Let me come back in here and just to illustrate, I'm going to just move this down. F of 2 equals 2 cubed is 8. So I plugged in 1 and I got 1. I plugged in 2 and I got 8. My intermediate value theorem says that since these numbers are not the same, there is some number in here, let's say pick between 1 and 8, let's pick 5. That means that there's a number between 1 and 2 that I can plug in, and it's going to give me that 5 when I cube it. So it just allows me to say, you know what, I can surmise that I can connect from here to there. All right, that's what the intermediate value theorem tells me. I'm not going to ask you to spit this back out to me, but mathematically you need to understand how we're able to do the things we're doing. Math isn't magic, it follows a set of rules. And the better we understand how things fit together, the better we are. Okay, symmetry review. You guys have done symmetry for the last unit. We have focused on even, odd, and neither. Notice I threw in another option. I have an even function if I plug in a -x and nothing changes. I get out the original function. My even function is symmetric about the y-axis. I have an odd function if I plug in a -x and I get the opposite of what I've started with. So every term changes signs. And an odd function, odd starts with O, it's symmetric about the origin. It's got that twist in the middle. Now, always before we skip number 3 and gone straight to number 4, if some terms change sign, but not everything changes sign, then my symmetry is not predictable. That's the correct answer there, not predictable symmetry. We have thrown in another instance, another case for quadratic functions. Now in 3.1 we learned about an axis of symmetry based on where the vertex falls, based on that horizontal shift. And quadratic functions are always going to be symmetric about that axis of symmetry. So we can use our vertex to find the location of our axis of symmetry, whatever that x-coordinate of our vertex is. Okay. New stuff. For our polynomial functions, smooth continuous curves, we have two types of behavior we're interested in. We're interested in end behavior, and then we are also interested in behavior at the x-intercept. So those are the two types of behaviors we're going to focus on in section 3.2. Because the domain of a polynomial function includes all real numbers, most of that function exists at the ends to the far right and left. To the far right and left, at the ends of the function. As the function heads off to infinity, it either increases, which means it's rising, or it decreases, which means it's falling, without bounds. It goes to infinity. Either positive or negative infinity. That's where most of the function lives. What we're interested in primarily, though, are the squiggles in the middle, our x-intercepts, but we need to know about those ends. So to know about the ends, we use our leading coefficient test. To use our leading coefficient test, we need to know the entire leading term. Now that leading term is the term with the greatest exponent. If sometimes my math lab messes with you and it doesn't put the leading term first, you're looking for the term with the greatest exponent. My leading term has three pieces of information. It has a variable, it has an exponent, and it has a coefficient. So every leading term has a variable, an raised to an exponent multiplied by a coefficient. Sometimes that coefficient is just 1, so it doesn't get written down and show up. Okay, that degree, that exponent, can be either odd or even. So we can have an odd degree polynomial function, or we can have an even degree polynomial function. That coefficient out front, part of my leading term, is either going to be a positive number, so I have a positive coefficient, or it's a negative coefficient, it's a negative number out front, which I know means that I have flipped it across the x-axis. So here's what happens. If I have an odd degree, so an odd degree, for example, would be like odd degree, leading term might be x to the third, x to the fifth, x to the 11th. Odd degrees. Odd degrees, the ends go in odd directions. One end goes up, one end goes down. One end goes up, one end goes down. Just like my odd function, symmetry is symmetric about the origin, so we got one end up, one end down. That's an odd degree polynomial. Now, if I have a positive coefficient out front, that means that those ends are going to be generally increasing. Stuff's going to happen in the middle, squiggles in the middle, but I'm going to start low and I'm going to finish high. It's positive. It's heading in a general upward from one end to the other of the function. If it's negative, though, it's going to be falling. It's going to be decreasing. Now, for my degree, it's even. If my leading term is x squared, 3x to the 4th, 12x to the 20th, even degree. Those ends are going to even out. They're going to go together. Both go up or both go down. They even out. If it's positive and if you're positive and you're smiling, your mouth, both ends go up. So if it's even and positive, both ends go up. If it's even and negative, both ends go down. I want to focus on the fact that when I'm doing these end behavior sketches, they don't meet in the middle because I got stuff going on there. And these are general cases. I don't know what stuff is going on yet. It depends on the individual function. So don't fill in, don't connect that's in the middle. Leave those middles blank. Now this leading coefficient test is going to be super, super useful for you. Make sure you've got it filled in. Make sure that you have it handy while you're doing your homework. All right, let's do some practice with this. Give the end behavior degree and maximum number of turning points for these. So we're going to identify the leading term. we're going to do 4 things. We're going to do leading term. We're going to do degree. We're going to do end behavior. And we're going to do maximum number of turns. Okay? Now, I don't think we've talked about that, how many times it can turn. Oh, we did. That was one of our characteristics back on the first page. There we go. Greatest possible number of turning points is up to 1 less than the degree. No more than 1 less than the degree. It doesn't have to turn that many times, but it can turn that many times. So let's see what we've got here. We've got 4 problems. Let's fill in our little chart. Leading term, it looks like they haven't tried to mess with us. None of these are factored. They're in general form. And they're in order from greatest exponent all the way down to least, which is the constant, which means I can circle my leading term. And the greatest exponent term is the first term in each one because these are in the correct order. It's not factored, so I can see my leading term. So for this first one, my leading term is 5x cubed. Here I have a negative 8x to the 5th. Here I have a 9x to the 4th. And finally, I have a negative 6x to the 8th. Those are my leading terms for each of these functions. Now, my leading term, you'll notice each leading term has 3 pieces of information. It has a variable, it has an exponent, and it has a coefficient. Those 3 things are key to each leading term. Degree. The degree is the exponent, the largest exponent on a term. So this is 3rd degree, 5th degree, 4th degree, 8th degree. From the degree, I'm going to skip a column, we know the maximum number of turns based on our characteristics is up to 1 less than the degree. So where I have degree 3, I have less than or equal to 2 turns. If I have a 3rd degree polynomial, it can turn up to 2 times. If I have a 5th degree polynomial, 5 minus 1 is 4. It can turn up to 4 times. It doesn't have to. It can turn 3 times or 2 times, can't turn 5 times. 4th degree turns up to 3 times, always 1 less. 8th degree could have 7 turns on it. Doesn't have to, but it could. All right, in behavior, that's based on those leading coefficient tests. So pull out that little square that we did. This one is odd, which means my ends are going to go in odd directions. My coefficient is positive, so overall I have an increasing function. So my ends are going to start low, finish high. Don't connect in the middle. Again, odd exponent, odd degree, so my ends go in opposite directions, but this time my coefficient is negative. So instead of an increasing function, I have a decreasing function. I'm going to start high and finish low. These last 2 functions, our leading term have even exponents, so the ends are going to even out and go together. Where it is an even exponent with a positive coefficient, both ends go up. And where it is an even exponent with a negative coefficient, both ends go down. Those are my end behaviors. So that's my first set of behaviors. The behaviors that talk about where most of the function exists, where those ends are heading off to the infinities. The other type of behavior on polynomial functions, behavior at the x-intercepts. Now remember, x-intercepts are also called either roots or zeros of my function. Anywhere I cross the x-axis. Every x-intercept corresponds to a factor of the polynomial. And there's my factor. My factor has an exponent. That exponent or degree on the factor is my multiplicity. Multiplicity is the exponent on the factor. Now if that exponent, that multiplicity, is odd, then at that value, at that x-intercept value, my graph is going to cross the x-axis. if that exponent is even, that multiplicity is even, the graph is going to touch the x-axis and turn around. It doesn't cross. And that's easy to remember because even numbers are divisible by 2, and this is 2 t's, t and t, touch and turn. So where I have a factor x minus a is my x-intercept value, multiplicity k. If that exponent is even, it touches and turns. If it's odd, it crosses. Remember, k is what? K is the exponent on the factor, which means I have to be able to look at my factors to know behavior at the intercepts, to know what those multiplicities would be. All right, let's put all this together and see what we've got. Okay. We have a polynomial function. We're going to give all this information. We're going to sketch our graph. Now, look at your polynomial function. Is that in general form? Well, general form would be multiplied together. I've got term plus or minus term plus or minus term, and it's not. It's being multiplied. I've got factors. Since I've got factors, I don't know my leading term. So let's go ahead and let's stop and let's acknowledge that we have this in factored form. If I were going to get my leading term, I would have to multiply the factors together. So we think about what that would be. If I were to multiply this, the biggest number, this biggest term would be x times x is x squared times another x, which would be x cubed. I know that to get this degree, to get this exponent, I would add up the exponents in the function. So I've got a 2 there and a 1 there. 2 plus 1 is 3. If I were to multiply it all the way together, I would have x cubed. There is not a coefficient other than 1 out in front either of those x's, so my coefficient here is just 1. I don't have to write that 1 down. But I understand my coefficient is 1, my variable is x, my exponent is 3. So what does this tell us? Well, this tells us I have a third degree polynomial. If it's third degree, I'm going to have at most 2 turns. End behavior. Well, end behavior, coefficient's positive, odd degree. My end behavior is going to be increasing. Start low, finish high. So we gave the degree, we gave the end behavior, we gave the maximum number of terms. Now we need to sketch the graph. There's a step to do between this and sketching the graph, and that is going to be your zero chart. And I always, always, always expect to see this zeros chart. You're going to have the same number of zeros as you do factors. In this case, I have 2 factors, which means I have 2 zeros. I want to know the multiplicity of each zero and what that means about the behavior at that zero. So I've got 2 zeros here because I have 2 factors. I want to think about taking my factor and setting it equal to 0. So x minus 5 equals 0. That gives me x equals 5. That is a 0 or root. That's where I have an x-intercept at positive 5. So let's look at that. 1, 2, 3, 4, 5. There is an x-intercept. The multiplicity on that factor, the exponent on that factor is 2. 2 is an even number. So that means that at that factor, my graph is going to touch and turn. So when I get to x equals 5, my graph is going to touch and turn. My other root, right here, if I set x plus 4 equal to 0 and solve, I get x is negative 4. That's the other value, 1, 2, 3, 4, where my graph is going to hit the x-axis at negative 4. Well, multiplicity on this factor is just 1. It's understood. 1 and 1 is odd. Where my multiplicity is odd, the graph is going to cross the x-axis there. So it's going to cross. I'm just going to put a C for cross. So at 5, we're going to touch and turn. at -4, we're going to cross. And I wrote those on there not because they're officially part of my graph, but so I don't forget. That's +5, that's -4. What else do I need to know in order to do a good graph? Well, I need to know a y-intercept. I need to know where I'm going to hit the y-axis. Y-intercepts happen where x is 0. So I'm going to go in here and I'm going to plug in 0 for x and find f of 0. So 0 minus 5 squared, 0 plus 4. -5 squared is 25. 25 times 4 is 100. So my y-intercept is 0, 100. That looks weird on my graph, but it's going to work. I'm going to do like a little break here because I can't get all the way if I count by ones. There is my y-intercept at 100. Make sure you include that on the graph. Okay, now we need to do our graph. Our sketch of our graph is going to start according to our end behavior. We're going to start low, finish high, make sure we hit all these points, and follow our behaviors. All right, here we go. Start low. I come up to -4 and I cross. I have to go all the way up to my y-intercept. I know I'm going to turn it back around because I've got another x-intercept here. For this x-intercept though, I just touch and turn. Touch and turn, go back up, and look at that. That was the end behavior I expected. Start low, finish high. All right, excellent. That looks really good. Let's, got a couple more pages here to wander through. We've got one more example of a graph, and then we talk about some details with our polynomial functions. Sorry, I messed up the light there. Okay, so once more. We've got factored form, so we don't know our leading term until we do a little bit of work. But I see that I've got 1, 2, 3 factors, which means when I set up my 0 chart, I'm going to have 3 roots or 3 zeros for my function, 3 x-intercepts. I always have to do this chart. 0, multiplicity, behaviors. That matters. Okay, so let's slow down. Let's do our leading term. To get our leading term, we need coefficient, variable, and exponent. My variable is x. Coefficient, 1x, 1x, 1x. So my coefficient is just 1. There's no negative out there. To get the exponent, I add up the exponents that are on all the factors. And don't forget that this is an exponent of 1. It's just understood. So 3 plus 2 plus 1 gives me a 6th degree polynomial. That tells me I'm going to have up to 5 turns, not more than 5, but up to 5 turns. And my end behavior, because it's a positive coefficient, even exponent, my end behavior going to start high, end high. All right, roots. If I set each of these equal to 0, if I set x plus 5 equal to 0 and solve, I get x is equal to a -5. That changes sign. Multiplicity on that factor is 3. 3 is odd, so it's going to cross at that value. X minus 3 equals to 0. That gives me x equals 3. Exponent is 2. That's my multiplicity. 2 is even, which means at that value I'm going to touch and turn. X plus 1 equals 0. X is equal to -1. Exponent there is a 1. That's odd, so I'm going to cross at that x-intercept. The only other information that I need is my y-intercept. Y-intercepts happen where x equals 0. So I plug that into my function. I get 5 cubed, which is 125, times negative times negative is a positive 9 times 1. So 125 times 9 times 1, that gets me to a huge, huge number. My y-intercept is at 1,125. So again, I have a break in my graph. All right, let's mark off. We need to go out to -5. 1, 2, 3, 4, 5. Out to +3 at least. 1, 2, 3. We'll go ahead and go to 4. I've got x-intercepts at -5. 2, 3, 4, 5. And I'm going to cross there. I've got one at +3, and I'm going to touch and turn there. And I've got one at -1, and I'm going to cross there. My y-intercept is way up here. So whatever my graph does, it has to make sure it hits all 4 of those points. Now, I want to point out to you that I have a multiplicity of 3 here. 3 is a cubic function. Exponent 3 is a cubic function. We know our cubic function does that wiggle, right? So that wiggle is going to be reflected when I cross the x-axis at this intercept. So let's see if we can check that out. We're going to use our end behavior. We're going to start high. We're going to come down here, and we are going to come in with a wiggle because it's cubed. And I know I'm going to need to turn around and come back because I've got more x-intercepts. And then I'm going to shoot way up high. Got to turn around and go back again because I have another x-intercept. This time I need to touch and turn, and then I end up going up again. Both ends are going up, just like my end behavior predicted. Where I had odd multiplicities, I crossed the x-axis. Where I had an even multiplicity, I touched and turned at the x-axis. All right. Let's look at our last bit of information that follows from this. Roots with multiplicities greater than or equal to 3 cause the graph to flatten out at that root. So we know our parent function quadratic, x squared, multiplicity 2, just opens up just so. Touch and turn opens up, multiplicity 2. If I had x to the 4th, multiplicity 4, it's still even, so it's still going to touch and turn. But when it comes in to touch and turn, it's going to slow down and it's going to widen and flatten out. So you see the difference between touch and turn, slow down, multiplicity 4. And if that even multiplicity continued to increase, that would continue to be reflected in the shape of the graph. All right, what about odd multiplicities? Well, we've got multiplicity 1 here, multiplicity 3, and multiplicity 5. Odd exponents. F of x equals x, that's just our parent linear function, zoom. It just shoots across. This is our cubic function, and it looks like this. Still crosses, multiplicity 1. Multiplicity 3, it slows down and flattens out some as it crosses. What do you think this multiplicity 5 is going to look like? Well, it's still going to be the same basic shape, but we're really going to slow down more and exaggerate that flatten out part so that you can kind of reflect that higher multiplicity. You're not really going to see this case much, but you are going to see these, and you need to note the difference. All right, last two, and then we're done here. Give the degree, the end behavior, maximum number of turns, and sketch the graph. G of x is factored, f of x is not. So let's start there. This is not factored. This one is factored. When it's not factored, I know my leading term. When it is factored, I have to work out my leading term. I have to think, okay, there's just one x, for 1 times x, 1 times x, but then I've got a 4th power and a 1st power, so that x to the 5th is going to be my leading term. All right, so that means this one is 4th degree. That's even and positive, so both ends are going up. I have up to 4 turns. No. I'm glad I caught that and didn't lie to you on the video. Up to 3 turns. It's one less than my degree. Over here, I've got 5th degree. That's odd. but the coefficient's positive, so in behavior is going to be increasing, and up to 4 turns, maximum of 4 turns. Alright, sketch the graph. Sketch the graph means we need to work out our zero factor, or zero, our roots, zero multiplicities, root multiplicity chart. So I need to factor this completely. F of x, I have a common factor of x squared here, so I'm going to pull that out front. That leaves me with x squared minus 4. X squared minus 4 is the difference of squares. I can factor that to give me conjugate pairs. Square root of 4 is 2, so x plus 2, x minus 2, and now I have that completely factored. Which means I've got 3 zeros because I have 3 factors. And I can do my behavior chart. I've got x squared is multiplicity 2, which means it's going to touch and turn. If I set that equal to 0, square root of 0 is 0, so that's x equals 0. For the next one, if I set that equal to 0, I have x equals negative 2, and for this one I would have x equals positive 2. The exponent on each of those is just 1, so I'm going to cross at each of those intercepts. Alright, let's work this out. We've got a 0 here, we've got a 0 at negative 2, and we've got a 0 at positive 2. I know my in behavior. I know at 0 I'm going to touch and turn, and the others I'm going to cross. So I need to start high, cross, touch and turn, come back and cross. Have relative minimums here. I don't know how they go, how far down they go. They may go way far down. We're not interested in that. We're interested in where we intercept the x-axis and what our behaviors are. This one is a little easier. We don't have to factor it. We can just do our zero chart. Zeros, multiplicity, and behaviors. We have 2 roots, 2 factors, so we have 2 roots. X minus 3 equals 0, x equals 3, x plus 2 equals 0, that gives me a negative 2. Multiplicity 4 and multiplicity 1. Behavior, that's even, so it's going to be touch and turn. That's odd, so it's going to be cross. I have an intercept at 3. I have an intercept at negative 2. Ooh, I need to work out my y-intercept here. My y-intercept here was at 0. But for here, my y-intercept, g of 0, is going to be negative 3 to the 4th times 2. That's going to be positive. Negative 3 to the 4th power is 81 times 2 is 162. So once again, we have climbed way up there, 162. My behavior, start low, finish high. I want to make sure I touch and turn here, and it's going to be a real slowdown when I touch and turn. I just crossed here, so let's do that. Let's cross, hit our y-intercept, come down, touch and turn, flatten out some, and then go back up. It's a little awkward, but we touched and turned, we flattened out because of that higher multiplicity. Alright, lots and lots of practice with polynomial functions coming up.